and other factors are also there, like shielding gases and wire movement. But the main dominant factor for lateral deposition is this voltage control. So if we can reduce the voltage by 1 or 2, then we can reduce we can control that lateral deposition. So I hope you have got the answer. So I'll start where I've ended. So sensitization I was talking about in the last session. So sensitization is particularly issue in austenitic stainless steel, where this chromium carbide formation is happening in the grain boundaries. One second, one second. Yeah, my pointer is this. So grain boundaries you can see here. This is the grain boundaries, and this uh, chromium carbide formation is happening in this grain boundaries. So there is rich chromium content in this grain boundaries, but adjacent to the grain boundaries, you can see this chromium depleted zone. This is the chromium depleted zone where at this position adjacent to grain boundaries, the area is susceptible to corrosion. You can see in this image the crack formation is there. So this is all due to this chromium carbide formation in the grain boundaries, and adjacent it is the depleted zone. So this is stricken by the transgranular corrosions and the other corrosion factors. So this is the weakest zone. So this from here the crack formation occurs, and it is susceptible to sensitization, or you can say weld decay. Weld decay is also the same concept uh, as sensitization. So how to mitigate the sensitization is the first, we have already talked about the L factor, this 30L and 304L, or 308 or 308L. The L stands for low carbon content um percentage, that is less than 0.03% weight percentage. And typically if we are not using L component like 304, it is having 0.08 percentage of carbon. So as the carbon content is reducing, the tendency of chromium carbide formation will be automatically reducing. So if chromium carbide is not forming, then it is very good for corrosion prevention. So other factors, we can use it as a solute, such as niobium, titanium, vanadium, and tantalum. So why we are using this is, if like chromium and carbon affinity is very high, so we have to replace that solute which is having a greater affinity than chromium and carbide formation. So niobium, titanium, vanadium, tantalum is having a greater affinity towards carbon content as compared to chromium. So niobium carbide will be forming a quicker bond as compared to chromium carbide. So this will replace chromium carbide, and we can avoid sensitization. So these things we can do it. And in the market now, we are getting stabilized stainless steel, that is for example 321. It's available in the market, which is titanium stabilized material. So we this is very good if we are not using L formation like 308 or 304L. So we can directly use titanium stabilized material, or we can use directly niobium stabilized material. We don't have to add any solute. Niobium is inbuilt in this. Niobium percentage is there in 347, SS347. So these are all austenitic stainless steel, which is non-magnetic in nature. So sensitization, this is the Schaeffler diagram of weld metals. So you can see all the phases: austenite, martensite, ferrite, how the chromium equivalent and niobium, nickel equivalent is working. So we can check at which position the chromium equivalent and nickel equivalent is merging and what phases are forming. So suppose if you're having the values in between this, that is the formation of austenite, or ferrite formation, martensite formation, that we can classify. So advantages and challenges in WAM processes. So this is very important, as in the first lecture I've already discussed. We are using a wire arc based system, which is using a wires, and wires are generally cheaper than powders. So as compared to laser, powder bed fusion, or any additive manufacturing which is having a raw material as a powders. So VAM is very economical in that terms. So the raw materials is very economical. So for example, 1 kg of steel, it's costing about 180 to 1300 rupees per kg for steels. And for titanium is also 9,000 to 22,000 per kg. This is for wires. The powders are too expensive. It is like 5,000 to 8,000 per kg for steel for 1 kg, and 24,000 to 68,000 rupees per kg for titanium powders. And it is increasing. The powder demand is increasing, so the cost is also increasing. And it is not about only 1 kg we have to use in powder bed fusion. It is like many, like 10 to 15 kg we need in a bulk. Then only we can fabricate a single component, which is also dimensionally constrained. So it is not that bigger component can be fabricated with this much kg of powders. So we need, um, that's why VAM steps in, and cheaper raw material can be used, and we can fabricate a similar component at a cheaper rate. So we can compare the price of the same product if we are fabricating with laser powder bed fusion, or a wire arc additive manufacturing using CMT or GMAW. So that will be a cheaper thing. So this is already I've discussed. Deposition rate are higher. For example, steels are deposited at a rate of 10 kg per hour in VAM as compared to 600 grams per hour in conventional additive manufacturing techniques. So there's a vast difference in deposition rate. That's why VAM is stepping in. So these type of defects you will see in the build direction for the VAM staircase defect. So this is all due to how we are controlling the path strategy and how we are controlling the process parameters. If we can control the thermal cycles and process parameters and optimize these parameters, so we can get a very good single wall structure and a multi-wall structure. Like this is example of a multi-wall structure. So this bead, this is the first bead, and this is the second bead which is adjacent to the first bead, and then again a bead. So three layers is being laid over adjacently. So you can see this is the reinforcement height. Bead height is called as reinforcement height. This is the bead width. This is the center distance D, which is the center of the two beads. And this is the how much we have to overlap, how much percentage overlap we need to get a very good multi-wall layering. So this is very important concept when we are fabricating a multi-wall component. A single wall, it doesn't have any impact, but in multi-wall, it is very important. The area of valley and overlapping area should be very specific. So you can see in the A diagram, if we are not overlapping, you will get this amount, this figure. So that is not needed, because in this the valleys are very the area of valley is very high. This is not needed. And you can see in the B figure, that means D is less than W. So D is the center distance, which is less than W, which is the bead width. Overlapping area is less than the area of valley. So overlapping area, if it is less, then also it is not good for the bead aesthetics or a multi-wall structure. So the optimum structure is the C point. So we can get a C thing by controlling the D. We have to make it as D less than W. So the center distance should be less than W. Suppose if your bead width is 8 mm, if we are optimizing the weld bead, and we know that at this process parameter we have a 8 mm weld width. So the center distance should be less than 8 mm. That means if we are making it as 6 or 5 mm, then the area of valley and overlapping area will be a optimum one, and we can get a very good multi-wall structure. So D should be less than W, and overlapping area should be equal to area of valley. So these two areas should be equal, then only this kind of structure we can get. Otherwise, these defects are not permittable. We have to get a very good bead aesthetics, because this is just a one layer adjacent to it. And again, we have to make a three bead structure, and then over and over we have to build this in the building direction. Then only a multi-wall cube or cuboid we can fabricate. Okay. So coming to the next slide, it's a defect associated with VAM. So there are two major related defects, as process related and material related. So process related is inhomogeneous structure and residual stress and distortion, and material related is solidification, cracking, and porosity. So with process related, I've already told in the first session, inhomogeneous structure, we will be getting inhomogeneous structure because when the thermal gradient is very high, because at the bottom layers and the top layers, there is mismatch in thermal gradients, then the inhomogeneous structure is has to be there. So but we have to possibly we have to reduce that by we can reduce that by heat treatment process after fabricating the component, if it is an inhomogeneous structure, like anisotropy is there, or properties are not mismatching. So we can get a we have to get a possible solution, that is post heat treatment we can do. That is very common. After welding also we have to do post heat treatment. The same is like in VAM also, we can fabricate and we can do a post heat treatment processes. And then another solution is work hardening followed by recrystallization, and then tailoring cooling rate. We can control the cooling rate. And Another solution is use of nanoparticles. So nanoparticles also helps in homogeneity. So if it is having a greater affinity with the layers, in between the layers, we can put a nanoparticle paste. Also nowadays, researchers are doing this. If we are laying first bead and we have made a nanoparticle paste, and um, we can paste nanoparticle we can put a nanoparticle paste on the first layer, and then the second layer is deposited on the nanoparticle pasted first layer. Then the integrity in between that inner layer will be very good, and that thermal gradient will be reduced by this nanoparticles, and then the delamination problem won't be occurring. And the inner layer heat affected zone will also be very refined, or very the structure microstructure will also look uh, in a in a like in a continuity we will be observing. So like columnar grains or equiax grains we can attain with that in the nanoparticles, with nanoparticles. So the second is residual stresses and distortion. Residual stresses, how we can reduce it? Like first we have to know which kind of residual stresses is are there in the VAM component. Suppose if there is a compressive residual stresses are not that much detrimental, but if we get a tensile residual stress, that is a very major problem, because it will the tensile residual stress will help in crack formation, or delamination problem will be there with tensile residual stresses. But if we are getting a compressive residual stress, that is okay. But both the stresses should not exceed its yield point of the material. If it is exceeding the yield point, then it is a very detrimental condition. Then the residual stresses has to be reduced. So how we can reduce it? The possible solution is post deposition heat treatment. Heat treatment is a possible solution. Uses of jigs and fixtures. We have to fix the substrate plate with very good jigs and fixtures, so that that much distortion or warping should not be there. Then only the residual stress will be coming inside. And other is follow proper deposition pattern. If we are making a deposition path correctly, and we are optimizing that path, then the residual stresses can be reduced. Sorry. So the other defects is material related, that is solidification, cracking, and porosity. Solidification cracking we can avoid by tailoring cooling rate. Cooling rate is a possible solution. Low heat input, as we have discussed, the cold metal transfer CMT, we can use as an alternative when the material is heat susceptible. We can't go with the GMW process. We have to use CMT with a low heat input. And if we are the other process, other solution is compatible alloying element. So alloying element we can add, and then solidification cracking can be reduced. And lastly, porosity, proper shielding we can offer. For porosity, it's a major problem in aluminum or softer materials. Porosity is very, it's a major problem in softer materials. Um, because entrapment of hydrogen or contamination leads to internal voids, and these things will occur with hydrogen embrittlement. So but that will be reduced by proper shielding. If we are proper, the shielding gas is around 15 to 20 liters per minute, then we can have a proper shielding, then we can reduce porosity. Or proper cleaning of the substrate material, and proper cleaning of the with a wire brush, we can clean the substrate material, and the wires also we can slightly clean it. And the possible last solution is tailoring process parameters. If we are, this is the major impact, like process parameters has to be controlled and has to be optimized only, then only we can reduce the level of porosity and we can get a bulk material. That's why the many researchers are having problem related to porosity in aluminum alloys. So many researchers, what they are doing, they are not um, following proper shielding, proper cleaning, and they are getting bigger voids in the aluminum alloy. So, and when they are checking the density, and the density is very much less as compared to conventional material. So the density will automatically reduce if the voids are there or hydrogen embrittlement will be there. So that we have to take care in the softer materials. That's why we have to give a proper shielding, proper cleaning, and process parameters should be optimized. Then only we can reduce these porosities level. This is the major problem. So we have already discussed these residual stresses and deformation. Stress generated are VAM, either longitudinal stress, residual stress, or transverse residual stress, resulting in bending, distortion. These things can be avoided by proper jigs and fixtures, that we have to keep it in mind. Porosity, we have already discussed major things: entrapment of hydrogen gases, suitable gas composition. We can get a pure argon if we are going for stainless steel or aluminum. We can use pure argon, 99.99% pure argon we can use. Then we can reduce and the porosity level, or we have to make the flow rate also to 15 or 16 to 20 liters per minute. Then we can possibly reduce it. Crack and delamination we have already discussed. Anisotropy I've already discussed in the first session, that the material properties in the bottom region and the top region will be different if the thermal gradient problem will be there. So in anisotropy, solidification and VAM support for the formation of microstructure containing large columnar grains rather than fine aqueous microstructure. Such columnar grains are formed on account of solidification condition favoring the epitaxial growth of with fewer nucleation events at the solid liquid interface. This epitaxial growth will be everywhere in the VAM component. Like when we are building in the build direction, like first layer and then second layer, the interface zone in the inner layer will be having the epitaxial growth. So that is the continuity in the microstructure region. If we take a cross section, if we can take a specimen out of that and check in the microstructure, we can check that continuity, that columnar grains. You can see here the transition zone. The columnar grains are growing upwards in the upward direction in the transverse, in the z-axis motion. So this is known as epitaxial growth. So the presence of higher temperature gradient and less growth rate at the solid liquid interface favors the formation of columnar grain morphology as shown in the figure. This is the figure. You can see the columnar grains here. So that's why how the properties can be changed, and we can manage with this. We can manage anisotropy by making a homogeneous material. If we are able to make a homogeneous material, then anisotropy will be reduced. That we want also. So how to improve? So there are every process have major problems and advantages and disadvantages. So VAM is also having these many problems, but how to improve the quality of VAM? So already we have fabricated like as fabricated component can be quality can be improved. So there are six methods, that is post heat treatment, post process heat treatment. Second is near immersion active cooling, NIAC, and third is interpass cooling, and then interpass cold rolling, and then hot forging VAM and ultra cold VAM. So post process heat treatment, everyone will be knowing like like normal heat treatment process, which will enhances the tensile strength, uh, refines grains and reduces the porosity. You can see in this image, the A image, figure A is the as fabricated component, and you can see in the B is the T6 heat treated condition. So we have made a heat treatment here, and we have seen as compared to A, B has limited, like very less porosity, like porosity has been reduced. And then the C condition is 23% hot deformed and T6 condition. So the T6 condition continues, and this is 23% hot deformation also taken place, so that to remove that porosities level. And we are seeing that this red portion and blue portion has been reduced. And lastly, the hot deformation has been increased and the porosity level is mitigated, like very less porosity level are there. So everyone has a problem in aluminum alloy. So like this author has done it. He has increased about 59% in mechanical strength of GTAW based VAM fabricated AA 2196, that is the 2000 series aluminum alloy. As built aluminum alloy was reported by this author. So as fabricated component, he's getting uh, some amount of strength, but he has increased that strength to 59% with this post process heat treatment. So that is very remarkable. So this has to be very good process. If we are getting a low strength, low mechanical strength and hardness, so we can go for post processing. Generally it is good for aluminum alloys, magnesium alloys and all. So the second thing is near immersion active cooling. It is basically we have to manage the thermal management thing. This image you can see, this is the normal VAM we are doing in the air, and this passive cooling you can see, it's they are keeping a fixed level of water or cooling liquid till the fixtures, and then above that it has been made, it has been VAM has been fabricated. So this with this cooling liquid, the heat will not be accumulated between the layers, it will be dissipated towards the liquid. And this is called as the concept of passive cooling. And the latest concept is NIAC, that is near immersion active cooling. So whenever you are building, so as you are going in Z direction, the water level is rising as per your Z direction level. So the as the levels are increasing, the the heat dissipation will be the problem will be sorted and no thermal gradient will be there, and we can get a very good VAM component. So with this near immersion active cooling, the result showed that with NIAC deposited wall, many researchers are getting best geometrical quality with the least percentage of presence of voids in porosity as compared to other two approaches or other WAM quality improvement this thing. So NIC approaches is provide proven to provide better mechanical properties with less anisotropy. So this also is a good solution to if the thermal gradients are too high, then we can use this solution to increase the mechanical properties and level of porosity we can reduce. So third is interpass cooling. Uh, Interpass cooling is a normal process, but we have a CO2 gas bottle within the side, and in every layer, when the interpass temperature has been set, then the CO2 gas bottle acts as a cooling solution. Like every layer has been like cooled, and we can maintain the interpass temperature in between. So complex thermal profile of VAM fabricated component involving repeated reheating and recooling cycles results in formation of complex microstructures and inferior mechanical properties. But in order to attain enhanced mechanical microstructure and enhanced mechanical properties, recently interpass cooling techniques are developed involving forced interpass cooling use compressed CO2 gas. So in every layer, they are pressing this CO2 gases, and we will be getting the layer will be cooled, and the second layer can be deposited, and again in the dwell time we can uh, push this CO2 gas, and we can cool the layers. So promising results were obtained in the initial study by these authors. So he has fabricated Ti6Al4 vanadium structure using forced interpass cooling and with CO2 gases, compressed CO2. So interpass cooling process was found to be producing refined microstructure, less oxidation, higher hardness, and improved strength. So microstructure will be reduced, like the if the grain growth has been restricted because of the interpass cooling, then the grain size will be reduced, and as the grain size is smaller, then the mechanical properties and hardness can be improved. So this is also a good solution for improving the quality of WAM. So next is one second. So next is interpass cold rolling. We can see there's a big roller over there, and if when we are fabricating the cold roller is a MIG torch or CMT torch, any torch that we are fabricating. So the torch is what it is doing is when we are making layers, the layer has a bulge over there. The top surface is bulgy. But what this roller is doing, it is plastically deforming this layers, and it is making us flat layers. So what plastic deformation is doing is it is reducing the porosity if there is some gas entrapment, and plus it is doing a work hardening, which is improving, which is it is forging and work hardening, which is improving the mechanical strength and reducing the porosity level. So the presence of thermal gradient within deposited layers and complex reheating and recooling phenomena in the WAM process results in the formation of anisotropy, microstructure, and mechanical properties. So interpass cold rolling of the deposited structure has evolved as another measure to significantly reduce microstructure and isotropy through the mechanism plastic deformation. So main concept here is plastic deformation of the deposited weld bead or layers. So uh, if the layer has just been deposited, it is in the solidus form, and this is easily you can plastically deform. The pressure or the weight of the roller depends, like if it is in solidus form, it is easily you can plastically deform. The pressure is not that much high, so it is very good solution to increase the mechanical properties. So interpass rolling of the weld bead has proven effective in the reducing the extent of residual stresses and distortion. Also, a hydraulically loaded slotted roller was made to move over the deposition with a constant speed, the same as GMW welding torch. It is shown in the figure. The use of roller was effective in reducing the distortion and surface roughness. Yeah, one more advantage for rolling this outer is surface roughness has been improved. Like it is making a flat bed type of thing. So one more advantage in this um, interpass cold rolling is to improve the surface roughness also of the deposit structure, and needed for machining in the final component was almost negligible. So it is very good, and refining this microstructure is the main output. So this author has been validated the concept of interpass rolling with Ti6Al4 vanadium material. So the ultimate tensile strength he has claimed like 876 megapascal, yield strength of 789 megapascal with an elongation of 11%. So it is very high as compared to the conventional Ti alloy, titanium alloy. So this is the betterment. This is the how the quality has been improving for VAM components. So the next solution is hot forging VAM. This is also a plastically deformed or plastically deformed or improving of surface roughness concept, where in the previous thing we are using a roller, and in this thing we are integrating a hammer within the torch. So within the torch, the hammer is there. There's the distance between the torch and the hammer, and whenever the bead is being laid over, then the hammer is striking the bead and making it as in plastic deformed. It is plastically deforming the material and making it as a flatbed. It is similar to the rolling condition. So novel concept. This is the novel concept of hot forging VAM is developed by this author, University of Caprica. This technique is designed with primary objective to utilize viscoplastic deformation behavior of the material at high temperatures to increase strength, reduce residual stresses, and homogenize grain structure. So, so this is also a betterment of FAM component, and you can see in the stress strain diagram, stress elongation diagram, the blue color region is the as-built uh, strength of the VAM, and you can see with the 55 Newton hammer, you can increase the strength by around 600. It is crossing around maximum ultimate strength, tensile strength is more than 600. So the increment in strength is there. So this is also a good alternative. And the last but not the least, it's a ultra cold VAM that is recently, this is a new concept in VAM. A new variant of VAM is developed by Rodrigues named ultra cold VAM, because like conventionally we are doing like this. The electrons flow is like this from this thing, GMAW process. And what he has done is he has integrated a wire feeder. So it's bypassing the electron flow, and it is reducing the heat affected zone. You can see the shape of the heat affected zone, the molten pool, heat affected zone and molten pool both have been reduced. Molten pool, you can see it is very much reduced. So as this has been reduced, so the coldness is also a comparative term. It's not a cold molten pool, but the molten pool size has been reduced so that we can get a colder or less temperature or low heat input layers can be fabricated. So to validate this process, a feasibility study has been done with HSLA steel. It delivers promising results and better arc stability, wall appearance, and avoid the formation of spatter. It is also able to increase cooling rate to 1 degree Celsius per second and significant effect on the microstructure development. So these are the six quality techniques how we can improve the quality of VAM. So first of all, we have to now we have to check how to optimize the weld bead, because for making a WAM component, we have to initially we have to start from the basics. We have to start from the different process parameters we have to set, and we have to set how we can get a so my screen is visible. Everyone can see my screen. Hello. Is the screen visible with the macros images?
Yes, sir.
Yeah. Is this visible?
Yes, sir. It is visual.
Yeah. Okay. Okay. So as in the lab session, Manish has already shown how the weld bead has been laid, and multi single wall structure or multi wall structure he might be showing. So how we have to analyze that beads, that is the major thing. Like these are the, you can see the bead images here. So this is the cross sectional uh, part of the bead, and you can see if I'm changing, you can see the bead, the penetration area, the substrate material also you can see. So how to analyze these things? So that is done by image software. How we can mark all the things in this. So I will show you one image in this. Yeah, this image. So in this image, you can see there are weld bead terminologies are being assigned. So this distance is known as the, one second, I will check the pointer. Yeah, this distance is known as the weld width, and the top height above the substrate material is called as weld reinforcement height, and this below the substrate material, the height, the depth you can see is penetration depth, you can say, or a weld penetration. And this angle, this inner angle or outer angle you can measure, that is known as a contact angle that we will measure now. And you can see one top area is marked as area A, and this is marked, bottom area is marked as area B. So why we are marking areas are because we have to measure the dilution, how much the filler wire is being diluted in the substrate material, that we have to calculate how much percentage is being diluted in the substrate material. So dilution is the penetration area divided by the total area of the weld bead. So area B is the penetrated area divided by area A plus area B. Area A and area B is the total weld bead area, that is above the substrate material and below the substrate material, total weld bead area into 100. That is the dilution percentage. So this is very important in WAM process, because if the dilution is too high means the penetration depth is too much. So that is not good for WAM, because the average length, average height of the layers will be reduced, and it should not be too less also. The dilution should not be too less, because if it is too less, that means the penetration is negligible. Only the substrate material you are seeing the weld bead, and penetration is negligible. So that will occur, that will having a problem of a delamination. So though both the two layers can be delaminated at any time, so that is also not good. So we will be calculating all the parameters by image software. Image software, it is freely available, and all the PhDs and postdocs are using this across the world. And this software is not only measuring this reinforcement area or penetration or length, or it is doing too much work. Like it can measure the microstructure grain size also. It can have a threshold images. It can generate threshold images also. It can have, it has a wide applications. So if you use the software, this is very good software, and you can use for your PhD thesis or postdoctoral thesis, so that you can use. Suppose I am taking one image and dropping in this. You can see this image has been opened in the software, and now we have to calculate how much is this thing, how much is the contact angle, how much is the area, how much is the weld width, that we have to calculate. So the first step is to maintain the scale bar. Without a scale bar, you can't study any image. If the scale bar is not in the image, you have to make a scale bar on your own. That the prior thing, you should know that the length of the uh, image that microscope has been taken. So that you can also take, like you can put a steel ruler uh, beneath the microscopic lens, and you can take an image. So how much is the how much distance is this length is traveling? Like suppose from this point to this point it is 10 so you can this distance, one distance you should know. So that can be calculated by putting a steel ruler in the microscope, and you can take the image and you can measure that. So first of all, we have to mark the scale bar on this image. It is already marked, but we have to mark, initially we have to mark, because all the microscope is not giving the calibrated images. All the microscope is not giving the scale bars and all, but this that we have taken in IIT Delhi, it is showing the scale bar, but we will be marking again. So first of all, we have to take a line command. From this point we have to press the shift command, and we have to drag the line. So this drag of line, you can see, you can see this line is being made from this point to this point, and this distance is known. This distance, I'm assuming we are knowing, and we can analyze it. We can analyze and go to set scale. Okay. So we can go to set scale. After set scale, you can see distance in pixel. From this point to this point, you can see 2592 pixels are there. But how much is the known distance, that you should know. Suppose I'm putting 10 and unit is 10 So 10 is the distance from this point to this point, and pixel aspect ratio is 1 only. And the scale is already made. You can see 259.2 pixels per So 1 contributes to 259.2 pixels. So if we are putting OK, then the software understands that this is having on the top, you can see this is having a 10 into 7.5 image. So this is 10, this is 7.5. The vertical distance is 7.5 and from horizontal it is 10 and it is in pixels also. Okay. So the software understands this image in the format you wanted to know, in the format, because initially the software only understands the pixels. So we again go to analyze. First we have done set scale. Now we have to do the tools. We have to put press on the tools, and then scale bar. Scale bar, and how much width of the scale bar you want to have, that is your priority. Like for example, some images, but all the images should be having a same scale bar distance. Like if you're keeping this image scale bar is 2 or 4 so all the images you should keep the same scale bar. So if we are putting 2 and scale bar should be at right corner, so the location is also we have to set lower right we can set. You can see the scale bar has come here, 2 mm, and you can mark it as black in color, and background you can say in white. So the scale bar is visible, and you can increase the font size also for the scale bar if you want. If it is not visible, then you can increase the size also. So now it is visible. You can see here, scale bar is visible, 2 mm. We have calibrated this image, and we have made a 2 mm scale bar. So this is the first thing you have to do after taking the macroscopic image. So after the bead has been laid, we have to cut the cross section and we have to polish it. This stage we are reaching after polishing only, because as a raw material we can't take because the surface is too harsh. So we have to polish it from 320 grit paper to 2000 grit paper, and we have to go for diamond paste polishing also. With diamond paste polishing, and then etching also we have to do etching with the, suppose if we are using aluminum alloys, this is aluminum alloy image. So you can use a Kellar reagent or Croyles reagent. So Kellars and Croyles if you're using, then you can see the penetration depth. So this is the wire is being diffused in the substrate material. So this image is to be taken after etching only. As a raw, as fabricated image, you can't take this type of images. So this image has to be taken after high grade of polishing and etching. So after etching, you can take the image and you can measure all the parameters. So after first parameter, we have to set a scale bar only. So scale bar we have set. So now we can measure all the things. So first of all, we will be measuring the width. So we are pressing this thing with this point to this point. You can check, and we have to press it Control M. If we are pressing Control M, we can get a length. So these data will be, you can save it as in Excel format also, or you can write somewhere in the Excel file. So this weld width has been measured as 4.167 mm. So this distance is 4.167 mm. Okay, so one parameter has been measured. Then you can, yes, then again we have to measure the penetration, the reinforcement height. So with Control B, the line is being stabled. You can see. So now I can measure the penetration reinforcement height. So maximum height we can take. So this is the maximum height, suppose. So Control M again I will put, and then you will be knowing that what is the height. That is 3.148 mm is the reinforcement height. So two things we have calculated. This is the this is the weld width. This is the reinforcement height. And now we can measure the penetration depth. Then again Control M. Penetration depth you can see that is 1.528 mm. So this penetration depth is 1.528 mm. So all the parameters you can write for a single process parameters. So now every image you have to do the same thing. So three parameters we found out. Now we can calculate a contact angle. For contact angle, we have to take the angle tool here. Angle tool we can take. We have to click here. 3-point touch we have to do. Again this, and we can make this angle. So angle has been made. Then Control M again we have to put. So angle is showing as 90.203 angle. So this is the angle from the outside, or you can minus it from 180 degree. You can get this angle, or we can measure from this angle. So both are contact angles. So this we can make it. So this is the fourth parameter. So this is the weld width, reinforcement height, penetration depth, and this is the angle, contact angle. So last is the dilution. So five parameters we have to know. So for dilution formula I have already told you. That is the penetration, area of penetration divided by the total area. So for dilution we have to use this freehand selection. This freehand selection we have to select, and then we have to drag this. We have to precisely drag, because like this small error can be generated. So at the last point you can leave the mouse button, and then you can see the closed loop has been made. So now we are pressing Control M now. So you can see area has been measured. So area is 2.627. So area is 2.627 mm square is the area of the penetrated zone. So now what we will be doing, we will be doing the total area. So again, the freehand selection we will be using. Sorry, again. So complete bead we have to capture. And the penetration area also. So full bead we have to capture. So we can leave that and then Control M again. So now you can see the area is coming out to be 13.814. So now you can calculate this thing. Suppose 2.627 divided by 13.814. If you calculate, it's into 100. That is coming out to be 19.01%. So 19% dilution has been made with this filler wire at this process parameter. So this is a single process parameter which is giving a 19%, almost 19% dilution. So this you can save the things, and you can um, make an Excel file out of that. All the parameters you have to calculate as per the process parameters, and you can measure it. So all the things you can measure. As I'm coming to the my slides. So suppose this is the design of experiment of the weld bead. Suppose we have three levels of voltage, and we have three levels of travel speed. So three levels means 22, 24, 26 is the three levels of voltage, and three levels of travel speed is 2, 4 and 2, 4 and 6 mm per second. So these three are the different levels of travel speed and three levels of voltage. So these are the two input parameters we are having, which is not dependent. So these are independent parameters. We can control the two parameters, and we have taken three levels. So in the design expert software, if we are putting three levels of one parameters and three levels of other parameter, so we will be getting a 13 output, 13 different combination with the CCD design, central composite design, that I will be demonstrating in the next thing, design expert software. So with increasing input parameter, suppose you want to take three parameters. The suppose voltage is there, voltage you've taken, travel speed you've taken, and again another parameter, suppose wire feed rate you want to take, or a gas flow rate you want to take, or other parameters suppose you want to take. So that parameter also has to be, suppose I'm taking a gas flow rate. So gas flow rate I can take 14 liters per minute, 16 liters per minute, and 18 liters per minute. So that the difference between the two levels should be equal. So it is not like that if you're taking 22 and 24 and then 25 you can take. So the equal distribution should be there. So difference between the two levels should be same. So if we are considering flow rate, then we can consider 14 or 17 to 20 also, 14, 17, 20, or 14, 16, 18 we can take. So if we are considering three process parameters and three levels, so we will be getting around, with central composite design, we will be getting 20 outcomes. So 20 different combinations we can make. So with this thing, this is the some MTech student work. So he has done two, sorry, BTech work they have made. So this is the three levels he has made and three levels of travel speed. So he got a 13 um, process parameter combination. So by this combination, he has measured, he has taken the cross sections, polished it, etched it, and then after diamond polishing, he has etched it also and taken the bead images and made a scale bar also, and he has measured all the parameters. Suppose this is the 13 parameters table is there, and he has calculated all the bead width. With all images, he has taken the bead width. There's the weld reinforcement or reinforcement height that we have already calculated. This is the contact angle. Then penetration height, penetration depth you can check. So he has calculated all the tables, and then area of penetration, then total area of the bead, and then dilution percentage. That is simply dividing the area of penetration upon total area. So dilution percentage can be calculated. This is the input parameter. So every parameter is having a different weld bead aesthetics. So what what is our ultimate goal is to find out the best parameter which can generate a best weld bead aesthetics. So after getting a best weld bead or optimal weld bead within the range of this design of expert design of experiments, so within this range of design of experiments, the optimum level of the process parameters if we can get, an optimum output if we can get, so with that optimum process parameter we can fabricate a vam component. So this is the prior study before the vam. So if we are not studying the concept of weld bead, then the vam, directly vam we can't do, because we have to know the nature of the bead at what process parameters the parameters will be changing, the contact angle, penetration, so everything will be having a different values. So this is the concept. This is the design expert. I will show you in a while, and this is the output. I will show you once again. So image software we have learned, and now we can cancel this. So the same thing you have to do for the all the images, and we can find all the 5 parameters. So it's easy, not a very difficult task. Image software. So now we will be starting the design expert software. Yeah, first I will start the design. So this is visible. Hello. The software interface is visible to you,
Yes, sir.
Vishal?
Yes,
Yeah.
sir.
Okay, okay. So whether we have to take a 5 minutes break, or I shall continue. because one more than 1 hour has been completed.
No issue, sir. You can continue.
Okay, okay. So for design expert, first of all, we have to make a new design. So the interface is very easy to understand. You can go to response surface. This is comes under CCD design is comes under response surface methodology, and CCD design full form is central composite design, and one more design is there, box Benkin. But central composite design is generally used for optimizing all the process parameters. Other optimization technique is also there. You can, if everybody knows, like genetic algorithm, artificial neural network, and any other optimization technique, or gray relation analysis, PCA technique, principal component analysis. So these are the major techniques that we can use. But the how we can get the optimum parameter, that is the ultimate goal. So if we are considering design expert, we will be going to central composite design. So here we have to put the numerical factors, how many input parameters you are having. Suppose if we are having a three parameters, so three input parameters we have we have got. We have to name it all the factors. Suppose voltage we are putting, then welding speed is the other factor, and suppose flow rate, flow rate flow rate of shielding gas I've taken as a third process parameter. Okay, so then we have to put the units. Flow rate liters per minute is the units. Then this is -1 is the lowest value of the levels that you are considering. Suppose in the previous question that my student has done 22, 24, 26. So these three are the levels. So 22 is the minimum, 26 is the maximum. So you have to decide the range. The range you have to decide with the prior hit and trial tests also, and where the bead is been very good or where the bead has been very bad. So that range, the maximum range you can take, and then you can optimize also. So suppose voltage I'm taking minimum 20, and 28 we are taking as a maximum value. And then welding speed, suppose if we are taking 4 per second, welding speed is the minimum value. And then 10 we are considering as the highest value. Flow rate, suppose 14 liters per minute, and maximum 20 liters per minute if we are considering. So these values um you have to attain these values, because due to the trial tests also. These values are, you can find out with the literature review, or you can find out with the intensive or extensive trial tests. And then we can put the values, the range values. And then we have to put whether we have to go for full factorial design or a partial factorial design. Then we, if we are having these much multiple outputs, like process parameters will be more in the full factorial design. And if we are having a limited raw materials or limited control over this, so we can go for a small or partial factorial design also. But by considering full factorial design, the optimum process parameter is good, and it is considering the whole, all the possible intensive factors combination. This software is ultimately, it is making a which process parameter combination is the best to get a best output. So full factorial design, I will suggest you to make it. And you can go to the options and you can see here it is written as 20 runs. So if we are considering two factors, then it will be showing as 13 runs. So in this 20 runs, you can see 6 values will be the repeating values. It is not like that all the 20 process parameters will be different. It is like I will show you in the next. One second. So this thing is important. You can see the replication center point you can control. That's what I'm talking about. That 20 runs, out of 20 runs, 6 is the central value. Central value means the central value of the voltage means 24 is the central value. Welding speed central value is 7, and then 17. So the central value combination is 6 times it is repeating. So that's why it is central composite design. So the central value is having the highest priority of getting a majority of the process parameters times. I will show in the design expert design of experiments. Then the alpha value you have to keep it as 1, because it's we are considering as central composite face center design. If you're taking other than 1, the k value, then the alpha value will be changing. Like it will be not like in between the uh, in between the range you have taken, like 20 to 28, the middle value is 24. If you have taken the value, the k value different, then the middle value will be changing. For example, 23.5 it can be going, 26.5 it can go. So that's why to keep as a central value, you have to keep it as face center design, and you can press OK. So now you can see the minus alpha and plus alpha is this one. Okay. So then you have to go for next. And this window is showing central composite design responses. So what are the responses you are having? All the responses you have to add. Suppose weld width is our first response, that is has been unit of mm. So 5 responses we are having. So weld width, after weld width you can weld reinforcement, that is also in mm. So penetration depth, that is in mm. Then contact angle is in degrees. And then dilution is in percentage. So these are the all the response that we have to calculate. Then if we can put as finish. So these are the combination that we have to make. So now we have to run the machine, and we have to select the combination 20 volts, 4 mm of welding speed, and 20 flow rate. 20 liters per minute is the flow rate. This combination we have to do first. This is the run distance, run pattern. Like first run we have to do this combination, then second bead we have to make this, then third combination, then fourth, like this we have to do. And after making all the 20 beads that Manish has already showed you how to make the beads. So after making all the 20 beads, you can cut a cross section and you can polish the sample. And then after polishing, you can take the image, and the macroscope image you can take with the 10 distance, and you can use images software to calculate all the these things: weld width, reinforcement, penetration depth, contact angle, and dilution. So all the factors, all the calculated values in the Excel file, you have to put in this. So all the things you have to put, and then the optimization will be starting. So which process parameter out of this is the best optimum process parameter to get a desired goal? Our desired goal also we have to set here in the optimization thing. So our goal is, suppose if we are, suppose for example, I'm taking uh, ultimate tensile strength here in place of these things. Ultimate tensile strength and second response if I'm taking a wear rate, and third response I'm taking as a corrosion rate. So suppose three responses I'm taking, and I have to optimize the process parameter in such a way that my goal is to uh, make the highest ultimate tensile strength with a lower level of wear rate and a lower level of corrosion rate. So this process parameter have to be optimized like this. So to get a desired goal that we want. So ultimate tensile strength should be maximum and wear rate and corrosion rate should be minimum. So that goal we have to set in this software, and with our desire it will calculate the all the process parameters and give the optimized results to you. So I'll show you the finalized thing. I will, 1 second. Oh, till this thing you have understood. So after this we have to fill this. We have already I've already one sample having. So you can open. Yes. So this is my MTech student from IIT Delhi. He has done the um, work in bonding of WAM component with diffusion bonding. I have shown his work in the first lecture in the morning. So this optimization he has done. So he has taken around 20, 22, 24 values, and 4, 5, 6 is the wire feed rate, and welding speed is he has taken 4, 5, 6 only. So these with this parameters, three levels and three factors, he is getting 20 outcomes. With 20 outcomes, he has calculated penetration, reinforcement, and dilution. So three responses he has calculated, and we are finding how what is the best parameter to get the desired outcomes. So what we have to do first, we have to analyze all the things. First, we have to analyze the first response. Here, penetration is the first response. We have to go to penetration. Then we have to go to fit summary. The fit summary will be showing. We have already optimized this, so I'm showing you the optimized work. So this is, it should be a quadratic thing because as per literature review and all the uh, literature available in on the net, so the penetration, reinforcement, dilution, everything is in quadratic phase uh, in the fit summary, in the model summary. So we have to maintain this quadratic values so that we can get a quadratic equation, and we can find out the within range. If we are selecting, we are not getting every parameter. Suppose from 22 to 24 there are n number of possibilities. Suppose 1 second, suppose if we are taking 22 to 24, we have taken just one voltage in between 22. But if we are saying like 20.5, at 20.5 voltage, and wire feed rate of 5.5 meter per minute, and welding speed of 5.5 per second, what is our output? So we don't know that, but the software is giving us the quadratic equation. With that quadratic equation, the model, we have to make the model significant, and we can extract the quadratic equation, and then we can play n number of times, like all the values we can calculate in the range 20 to 24. N number of possibilities are there, n number of combinations of process parameters will be there, and that we can calculate all the responses. So it is also predictive modeling. Suppose we don't know 20.5. At 20.5 voltage, what should be our weld width, or where penetration depth, what should be our penetration depth. But the modeler software knows that. So if we are putting the value of 20.5 and the input parameters, if we are putting, then the equation will be giving the output. The penetration equation will be shown. So that I will show you here. So first we have to go to first factor analysis part. First factor is penetration. Then fit summary. Fit summary should be quadratic. Then model. All the in model, everything should be included. Everything means A represent voltage, B represent wire feed rate, C represent welding speed. So the combination of these are also important. So voltage into wire feed rate, that is AB combination, AC combination, BC combination, and then the square root also, squares of the input parameters. So A square, B square, and C square. So as it is following a quadratic equation, we have to make the model till this only. So we have to go for ANOVA. So ANOVA table is in front of you. So how we can read these things are, so this F value is very important. F and P value are very important. F value stands for Fisher value. That represents the model significancy. And the dominant factor, which is the dominant factor which controls that output. So every output has been controlled by a dominant input parameter. So that I will tell you. P value is the probability value. Probability value should be less than 0.05. If it is not 0.05, less than 0.05, then that factor is not significant. As we have already in the BTech times, we have understood 95% confidence level interval. So that 5% is the negligence rate. Sorry. So in the software also, it is showing the p value should be less than 0.05, indicate model terms are significant. So all the values for this, suppose voltage, wire feed rate, and welding speed, all AB, the combination of AB, AC, BC, A square, B square, C square, all the factors should be less than 0.05. If it is not, if one or two factors are also missing, then those factors are not considerable. So we have to make that thing, we have to make that significant factors. So that I will tell you how we have to make it. And that's residual thing. This is the residual part, that is lack of fit, which is the 5%. That is should be more than 0.05. This is 0.0627. That is not significant. So this is how the model has been made significant. Okay. um, yes. So this F value you can see. So F value of model is 148.51. Voltage is 666.86. Wire feed rate is 455.68. And welding speed is this. So if we, one more column we have to add is the contribution percentage. So which parameter, how we have to find the dominant parameter is, we have to, suppose we have to um, check the contribution of this voltage. So voltage is this F value divided by the total values of this in the significancy mode. So we have to divide 666.86 divide by total value. So we can put it in this Excel file, put this values in the Excel file. We can we can calculate all the values and we can divide by 666.86. So it will come around, it will come around the highest value. Suppose if we can calculate, so we can understand with the F value, the voltage is the dominant factor. So how much percentage, that we have to calculate with the formula, with this value divided by the total value. Suppose if we want to calculate the contribution level of wire feed rate, we can measure 455.68 divided by the total summation of this. Okay. So that how we can find out the percentage contribution of all the factors and the model also. So how the model is contributing. So with seeing the F value, we can see the voltage is the dominant factor for penetration. For this is only one response. This is the first response, that is penetration. So we can say that uh, if we are changing specific voltage, if we are changing voltage from 20 to 20.2, the penetration will be changing rapidly. So this is the governing factor or a dominant factor in terms of penetration. So this is the input parameter. How, if we want to control the penetration, then we can control the voltage levels. Okay. So this how we can find out which parameter is influenced with without which output is being influenced with the which parameters, input parameters. Okay, so this is the fit statistics, that is precision r square value that should be equivalent to 0.9 or 0.8, more than 0.8, that you will get from here. Adequate precision. So, and this is very important. This actual equation, we have to put it as actual equation, and the actual equation is this: penetration is equal to minus 20.565 plus 1.37 into voltage plus 2.81 into wire feed rate. So this is the quadratic equation, and this we can uh, the system is giving, the software is giving that if we are making this penetration formula, and now we can calculate at the uh, in between process parameters. Suppose 20.5 we have to calculate, we will be putting voltage value is 20.5, wire feed rate as suppose 5.5, welding speed as 5.5, and then we can calculate the penetration value. So it will be giving the penetration value as per the model significancy. So we can go to diagnostics and model graph. So this is the contour graph we are getting. So this is the wire feed rate and this is the welding speed in the y direction. So the red portion indicates that the penetration is higher at this side, and the green portion indicates the penetration is lower at this side. So red portion means if we are increasing the wire feed rate and decreasing the welding speed, so this portion can be attained. Increasing the wire feed rate and decreasing the welding speed, we can attain this penetration, higher penetration. Or how much we have to calculate, how much we have to control the penetration, we can decide as per the combination. So with this combination, with the BC combination, it is wire feed rate and welding speed. And here we can change the combination. We can take the graph as AB also. AB means A means voltage and B means wire feed rate. So this combination happening is this: we have to increase the voltage for higher penetration and increase the wire feed rate. So this portion, the red portion, will be, you can check. So higher penetration can be attained by increasing the voltage and increasing the wire feed rate. So how we can increase or decrease the penetration value, then we can calculate from the graph. And this is the AC thing, the voltage and welding speed. So we can increase the voltage and decrease the welding speed, we can get a higher depth of penetration. So these are the combination of this contour graph. And then one more graph is important, that is interaction zone. The interaction of voltage and penetration we can get. Then voltage and penetration, and this voltage and penetration when keeping the welding speed constant. And this is wire feed rate and penetration combination when keeping welding speed constant. So this interaction we can get. And again, one important graph is predicted versus actual. So this is the predicted values, and predicted values are the single line, black line, and this dotted points are the actual values. So actual values are almost in sync with the predicted value. So that means our model is significant. and we can trust this model, and we can calculate the values of penetration, other factors we can optimized. So one more graph is important, that is 3D surface. So this 3D surface graph is important. You can see here. So for this combination, this is the AB combination of penetration, voltage and wire feed rate. So by increasing the voltage and decreasing the wire feed rate, increasing the wire feed rate, you can get a higher penetration as per the this surface model, 3D surface model. And you can change the combination, AC combination. You can see how we can analyze these things. Then BC. So this all is for the penetration thing. We have just analyzed one factor, one output factor. It takes time, but the optimization can be done easily. It's it's very easy optimization. Then by then we can go for second analysis, that is reinforcement. Then again, fit summary, this should be quadratic model ANOVA. You can see the ANOVA table p value is very less than 0.05 values have been there, and lack of fit is not significant, that is 0.05, it is more than 0.05. And you can see reinforcement, the second output that we have done, the second output is the F value is maximum for wire feed rate. So now you can say that wire feed rate is the dominant factor for reinforcement. So to influence the reinforcement, you can minorly change the wire feed rate. So by controlling this, by changing slightly the wire feed rate, reinforcement can change rapidly. So these factors is very important factor, dominant factor, which factor is dominant and which factor is influencing which output, that you should know. And again, the actual equation is this reinforcement. We will be getting the reinforcement quadratic equation that we can calculate in the intermediate values. And there's the diagnostics and then model graph. Model graph, this is the contour graph. We can get all the combination here, AC, BC. So by increasing the feed rate, we by decreasing the welding speed, we can get a higher reinforcement values. So this 3.65 is the minimum and 5.41 is the maximum value. So this is controlled by this. And then the interaction, same interaction curves are there, so that you can analyze how your influence parameters are influencing the output parameters. And then the surface model graphs are there. This is the 3D surface plot of AB, then AC, then BC. So these are the factors. So again, the third and the final thing is dilution you can do. Again, the same steps you have to make. Quadratic model ANOVA should be, P should be less than 0.05. The same thing we have to make it. And now you can see voltage and wire feed rate are almost same, like almost have a higher F value. So you can say that uh, wire feed rate and voltage both are the dominant factor, or you can say the major dominant factor is wire feed rate for in terms of dilution. So the same equation, dilution equation is there. So you can measure all the values. So the same contour graph, we can say the how the dilution can be increased or decreased. So this is the AB combination, then AC combination and BC combination. Then interaction, all the things are same. You can follow the steps, and then 3D surface plots. For all the factors, you have to give the justification that how and why it is increasing and decreasing, that is the main thing that you have to evaluate. Okay, so after analyzing all the factors, suppose in this optimization, my student has taken only three: penetration, reinforcement, and dilution. But in the initial thing, I've shown you contact angle also and weld width also. So all the factors you can take in the same stage. So after analyzing all the things, you can go for optimization. This is just the analysis part. Now the actual optimization will start. So before that, I have to tell you, like, initially I've told you like six values out of 20 will be same. You can see here like 22, 5 and 5, and 22, 5 and 5. See, the factors are same here, 22, 5 and 5. This, the middle value will be repeating itself six times. So that's why 20 combination, different combinations has been taken, 14 different combinations, six as the repeating combinations. So that's why this central composite design works on repeating its central value. So after all the analysis part, so then optimization we have to do. Then we have to click to numerical optimization. So voltage, all the factors will be coming here: voltage, wire feed rate, and welding speed. These are the input parameters. This you don't have to set the goal. So what goals we have to set? That is our criteria. What we want. If we want to fabricate a VAM component, so what we need is penetration should be what. So penetration should be our goal is to penetration should be maximum, minimum, target value in range. So that we have to check. So our minimum value is 0.74 and the highest value is 2.48 with the calculation part. So suppose if we take in range combination, I'm taking 1.25 or 1, I'm taking 1 to 1.5 is my limit. So apart from in between this penetration value, this I will be very much happy if the penetration falls in between this 1 to 1.5. So that we have to set a goal as per your literature survey or your VAM component. That is your experience. So with my experience, I've taken the penetration range of 1 to 1.5, or but this we have to consider, we have to take into consideration that the delamination should not be there. uh, because if we get a lesser penetration, then the delamination could be there. So that this should be an optimum thing. The 1 to 1.5 have taken, and within this range we have to take. Okay, so that you have to check. And then suppose reinforcement is the other factor. What is our goal? So reinforcement can be maximum. Reinforcement is the height of the reinforcement height is the top level height that is above the substrate material. So that could be maximum, but I've taken in the range of 4 to 5 because our minimum is 3.65 to 5.41. That I have taken 4 to 5 value, that is 4 mm to 5 mm in between reinforcement. If it is in between this, I will be the optimum values I can get. And dilution, lastly, dilution. So dilution is minimum with this factors are 17.18 and 44.51. So I've taken the dilution as 20 to 25%. So with this goal, these goals we have to set. So these goals we have to set. By after setting these goals, we can go to solution. So solution will be provided with the software itself. So what solution he has take here, the software has given is the our optimum result, like desirability is 100%. That is one is means 100%, and solution is 1 out of 25 solution they have given. And the first solution is this. So the optimum result the software is giving is voltage is 20.122, wire feed rate is 4.19 and welding speed is 4.08 So this is the input parameter, input optimized parameter that we have to consider while making an optimum weld bead. So if we again fabricate with this combination, we will get the output of this penetration we will be getting as 1.13, reinforcement we will be getting as 4.0695, and dilution almost 25%, 24.96%. So while keeping these input parameters, we will be again go for confirmation test with these parameters, and we will be getting the output by this or around this. It should not be like major difference between this output and your output. So that is the confirmation test we have to do at the last. So this is the 25 solutions. So this is the first solution. Second solution is this: if we can go for voltage 20.2, 4 and 4.13, and we can get multiple combinations, but it will be around same thing. So the first solution you can take and you can stick to that, and graphical representation you can go. So this is the desirability, that is 100%. So this can be achieved easily. Desirability should be 70, above 70% to reiterate that. If it is below 50% desirability, then you can't reiterate, because suppose the software is giving the results, and if you are actually confirming with the actual making the bead, the results won't be matching. So that desirability should be high. Then only you can reiterate the same things. Okay. So the same thing is with the optimized parameters. 3D contour graph are here. Interaction curves are here. You can calculate all the things. You can download and this thing. And this is the graphical representation. So this is the 25% dilution, reinforcement 4, and the combination. The penetration is 1.13, 4.06, and 24.97 is the dilation, and this is the graphical representation of wire feed rate and welding speed. So is the overlay plot. So this is our complete optimization, and then we can go for post analysis. This is the point analysis. Post analysis we have to do for the confirmation test. So how we can confirm that this output, this optimized parameters are correct or not. So that we have to check. So we have to again go for the experimental setup, and we have to make the same combination of bead for this. For this input parameters, the voltage is 20.12, wire feed rate of 4.19, and welding speed of 4.08. So this combination we have to try, and experimentally we have to put the values, and we can make the things. And our result should be almost like this. Penetration should be 1.13, reinforcement should be this, and dilution should be this. Okay. And then we have to go for confirmation test. So while experimenting, you are keeping these values. So we have to put the values, what we are getting, that we have to put. So 3 times we have to go for confirmation test. The same in the optimized parameter, you have to make 3 beads, and then all the 3 beads has to be cross sectioned and check the penetration, dilution, and reinforcement. My student has done that. So his results are this: 1.17, 1.11, 1.15, and reinforcement are this, and dilution is this. So all the things he has made it, and then so it confirms that our input parameter are the optimized one. So because I reiterated the values, and it is coming almost in the same scale. So this is the coefficient table that we can see here. As p values are less than 0.05, it will be all the model will be significant. So this is all for the optimization thing. And one thing I want to tell you, uh, if suppose in the analysis part the fit summary is not quadratic, what we can do? Suppose it is cubic or linear or 2fi or ANOVA table. If we are getting the some values to be, suppose majorly we are getting 0.05 less than 0.05, but suppose two or three parameters are above that 0.05. So what we can do? So don't worry, that is not a major question, major problem. Just we have to check that. Suppose in penetration, one value is higher. Suppose any value is higher in penetration than in penetration analysis part. So this is the actual reading that we have got. So we can minorly change. Suppose 2.1 it is showing. So we can keep it as 2.11 or 2.12 or 2.09 or 2.08. So this minor adjustment we can do to make the model significant. Some hit and trials we have to do. Otherwise, by calculating the graph, some error could be in the calculating the reinforcement penetration or dilution zone. So that error we have to take into consideration in this model significancy. So suppose this 2.1, how far we can justify that it is a correct measurement? Because we have taken the macro image, we have measured the penetration value, and what we are doing is we are manually measuring it. Okay, so but 100% we are not sure that it is 2.1 or 2.11 or 2.09. So that minute error will be there. So that you have to take into consideration while optimizing the process parameters. So if it is not coming in the range of p values less than 0.05, you have to change the in this readings you can change the values, or suppose in the reinforcement it is not coming, you can change these values, but not majorly. You have to change very less, like 0.01, 0.02 you can change, minute values you can change. So while changing, all the factors will be changing and the p values will be in the range. So that is very easy to do it. So this is all about the optimization of design expert. So we can get the output of the design expert. So mm, one second. So these are the outputs we can get. This I have already told. Suppose in this you can see in the bead reinforcement, the AB value is not a 0 point less than 0.05. So what we can do? So we can go to bead reinforcement column and we can adjust that readings. So just minute change if we can give, these values can be then these values can be controlled to 0 point less than 0.05. So it is not a big problem. We have to sit and we have to make that in controlled model significance. We have to make it. So this is all about contact angle, penetration, dilution. So what we have to do is maximize or minimize the optimized criteria. This criteria you have to decide. So that is your experience or your output, what is to be calculated. So this is the optimized factors. So this is, I think, all about design software and all. I think I've covered all the bead process parameters, images software, and how we can calculate the bead aesthetics and all, and how we can optimize the process parameters. So if any questions are there, I'm there to answer that.
Anyone who has any questions, please write it in the chat box.
So I think now design expert and CCD design will be easy to the students. I assume that students have learned something or something that from my lectures.
So there was a question at 10 a.m. in the morning session by
Yeah,
Pankaj
that
sir.
I have, yeah, that I have answered, I think.
Okay, sir.
In the starting of the lecture, he has asked about lateral deposition, I think.
Yes, sir.
Yeah, that I have answered in the starting of the lecture.
So we have another question.
Yeah, tell me.
Thank you very much for a nice conversation on design factor. My question is,
Yes.
presently contest design expert software is utilized for the plastic quartz watches manufacturing because plastic quartz watches non-manufactured in India came from Hong Kong or Thailand or South Korea or Japan. So there is a possible design of plastic. It is possible like a design in studio for the plastic quartz watches manufacturing.
So your question is, we can use design expert for plastics.
Yes, sir.
Yeah, we can use for any other material. It is not limited to metals only. So whatever the input parameter you are getting and you are putting and the output you are getting, just the software just deals with the input and output parameter. Just like the other optimization technique as ANN or genetic algorithm or other optimization technique deals with the input and output parameters. And what optimized input parameters will be there to control the output. So it is not like dependent on material. It can be plastic, metals, anything we can do.
Okay, sir. Thank you. We have another question, sir.
Yeah.
Yeah, thank you so much, sir, for the nice presentation you have.
Thank you.
Just I would like to confirm that whether
Hmm.
the validation of this model,
Hmm.
this model is validated through the confirmation test, right?
Right. Yeah, without confirmation test, you can't put the values any other, or you can't publish it. With confirmation test only, we have to confirm that our optimized parameter is confirmed. Like the output, you have to what output the software is giving and what output you have got with the optimized parameter. That has to be correlated, and if it is in range or it is very near to the software giving data, then you can confirm that this is the actual optimized parameters, and then we can publish it.
So, if whatever the data we are getting from software, if